Hmm. Okay. All right. So let's do this. So welcome again to the is it the third installment?
Third.
The third installment of Dance at Cohesa Get to Know the Team series. Today it's a pleasure to have two presenters. One is from U of T, Carusone, who works on circuits, and the other one is Arrvindh from Simon Fraser University. We're going to continue with that. Let's do 10 minutes of presentations and then Q&A if we have many. We understand that this is final weeks for many, and we're close to the Christmas break as well. We will probably it's going to be the last for 2017, the last seminar for the 2017. We're going to resume in 2018. We're going to follow up with the details. So thank you all for connecting today. And Tony, please.
Sure, yeah. Maybe I'll just pop into the camera to say hello, and you get to see my face now. And yeah, thanks for joining us virtually. So I'll just do a brief presentation of summarizing a little bit about me and a little bit about my lab's activities. So this is first, I'll just get the personal stuff out of the way right at the beginning. So I arrived here at U of T in 1992 when I was 17 years old, and I never left. I did both my degrees here, and then joined as a faculty member, actually a little bit before my graduation even. So I've never left since I was 17 years old. Happy to still be here. I also, in addition to doing all good things a professor should do, I also am a consultant for semiconductor companies, both local startups, Genum, Intel are some local companies around here. Intel, I spent some time in Portland, Oregon as well on my first sabbatical, Rambus, and more recently Huawei. So yeah, I like to stay active with local industry as well, to stay relevant to them. This is a book I co-authored. It's actually quite used quite a bit across North America for graduate level analog integrated circuit design. So I'm known by a lot of people for that. This is I like to spend time here. This is my cottage near Parry Sound in Ontario, and these are my 3 kids here this Halloween. That's a little bit about me. The next slide here just gives a little summary of my lab's activities. So basically in my lab we focus on custom silicon integrated circuit implementations of signal processing functions, which is intentionally broad. I like to be pretty broad in my activities. Right now I've got 8 PhD and 5 master's students in my lab. So just to give you a flavor for the research we do, every student project will typically begin with some system modeling, and we do that either in MATLAB or Python or some behavioral language like that. And in doing that, we usually identify specific IC design challenge of interest. And then we do detailed IC design on that. It could be analog and or digital. And we always develop prototypes. We have prototypes fabricated by external partners. And we even try and incorporate them into demonstration platforms. So here's an example of a chip designed by a student. We get a package, we do some testing in the lab, and a student will typically also produce some kind of, I call it a demonstration platform, but it's basically all the printed circuit board components, the software, the drivers, or whatever that's needed to show it doing something useful. That's the typical flow for that each student will go through in my lab. And after they graduate, the students in my lab typically go on to do R&D in the IC design industry, I think. So far, every one of my students has continued to do IC design, a couple of them in academia, and most of them in industry. So that's just a high-level overview, and then I'm just going to, by way of example, just go through a couple of example projects in my lab so you get more of a feel for what we do. This is one recently completed project on next-generation memory interfaces. So here the idea was to work on the density of the memory interface. So we're trying to imagine an application where there'll be an ASIC flipped onto a silicon interposer alongside some kind of memory chip or memory cube even. It's a 2.5D integrated platform, and we're looking at the circuits that are needed to transmit and receive data at very high speed and with very high density over that kind of interconnect. So we developed some transmitter and receiver circuits that are very compact and that could work over that particular type of interconnect really power efficiently. And then we developed the prototypes of the transmitter and receiver circuits in 28 nanometer CMOS. So these are 28 nanometer CMOS dies. And they were flipped onto this silicon interposer, which was also designed by my student Behzad. That's in an older CMOS technology, but really there's no transistors on this one. This is just providing the interconnect between the two dies, the two 20 nanometer dies. And you can see we looking at what are the implications of having longer interconnect. So you see some serpentine traces here connecting the transmitter and receiver. Here's the finished prototype. You can see the backside of the die split on there. And we were able to demonstrate very dense I/O compared to the prior art. We were ultimately communicating at 20 gigabits per second per wire, or per bump, if you like, over the interface. So that's quite a high bandwidth density of almost a terabit per second per millimeter squared die area. This is a different project here. This is still ongoing. We're looking at, I'm interested in non-uniform quantization actually. So typically analog to digital converters are designed with uniform quantization, but we know that that's not the optimal quantization for non-uniformly distributed signals. So we're interested in this question of how should the optimal quantization levels be found. The Lloyd max quantization is a well-known, it's been well-known for a while, method to quantize a signal in a non-uniform way that minimizes the mean squared error of that quantization. But minimizing the mean squared error is not always what you want. Some types of errors can be tolerated by the system that it's in. Some types cannot be tolerated. So, for example, when we're doing digital communication, what we really care about is the link bit error rate. We don't care about the mean squared error, only insofar as it determines the link bit error rate. So we worked on methods to select the levels to minimize the bit error rate of the link in that case. And we have to look at how we have to implement the analog circuits and the subsequent DSP so that we can make use of that non-uniformly quantized data in the best possible way, the most efficient way. And also another interesting part of the research is to be able to dynamically, while the system is operating, recognize when it can benefit from some different kind of quantization, to automatically do that so that it's always operating with the best efficiency possible. This is just a little cartoon sketch here. This was actually measured in the lab. There's an A to D converter, very high-speed A to D converter, and the input data that it was sampling was distributed in this funny way because it's a digital communication signal. And then we had our algorithm running, and it automatically identified the quantization levels shown in blue there, and eliminated all the other quantization levels to save power. And it did so with no appreciable loss in performance. So that's the kind of flavor of that research. And so again, through doing that, we did some system level modeling, and then ultimately, an interesting challenge is how do we design an A to D converter that can actually dynamically change the quantization levels and still be efficient all the time. And so this was Luke's project, and it's accepted for presentation at ISSCC in February. So basically, it's a 32 gigasample per second A to D receiver that's meant to be at the front end of a digital communication receiver. And we made the prototype in 16 nanometer FinFET technology, so that was exciting. We've done 2 prototypes so far in 16 nanometer FinFET, so we're getting more experience with that. So the A to D basically has 6 bits resolution nominally, but each individual quantization level can be disabled to decrease power consumption. So when the channel that we're communicating over is really benign, then we can get away with many fewer quantization levels and use that to save power. And we showed in this paper that by optimizing the quantization levels that we use, we can save a lot of power by doing that. So basically the circuits here in the front end are designed in such a way that if you do turn off quantization levels, you start saving power right away. So for example, LR means it was a very long, difficult channel. So in that case, the circuitry was consuming 280 milliwatts. But for a very short channel, VSR, very short reach channel, which is a very benign channel, the power scaled right down to 100 milliwatts. So that was kind of interesting in this research community of wireline receivers. Usually you over-design everything for the worst case, and then you can realize only very minimal power savings for the other cases. So this is very aggressive power scaling with the benefit in that application. So that's actually still ongoing. We're still pursuing that a little bit. This is an older project, but I thought it was a little bit pertinent to Cohesa themes. So basically, this was done quite some time ago. We're interested in error control coding and making efficient hardware decoders for that. The type of code we're looking at is a low-density parity check code. So decoders for that type of error control code perform iterative computations on a very large and random-like graph. So the real graph would be much, much larger, like 1,000 nodes or even more in the graph. But the idea is there's 2 types of nodes. There's check nodes and variable nodes. And the decoding proceeds by iteratively doing computations and passing messages back and forth between them. So the check nodes will perform one type of computation. They'll pass the result of that to these other variable nodes. The variable nodes will perform a little different computation and pass the results back. So the signal flow proceeds like that for several iterations, anywhere from 5 to even 100 or more, and you get the result at the end of it. So the way to map that kind of signal processing into hardware is two popular ways to do that. One is to pass messages through a shared memory structure. So the check and variable nodes are both accessing this memory and passing their messages via it. The challenge is then, you've got this bottleneck in terms of memory access that can limit the speed. And higher speed had been demonstrated with a fully parallel architecture where basically you've got all the variable nodes, all the check nodes there, and they're just passing messages back and forth to each other. So the messages are still stored in a kind of a memory, but it's like a distributed memory where every node, compute node, has its own little register that just sort of stores the result of the last computation. And then the challenge in those, although they were, had shown faster performance, but the challenge becomes scaling it up to very large graphs. The routing congestion just made it impractical. So those had not been demonstrated at very large block sizes. So what we did there was we looked at bit serial message passing to try and alleviate the routing congestion so that all the messages would be sent over one serial line. So it slows things down a little bit in terms of, you need n clock cycles to communicate an n-bit message, but still, that's not that much slower than what's needed to read and write from memory. The memory bottleneck is comparable to that. And then it afforded some other interesting advantages. For example, we could play with gear shifting, by which we mean, it turns out you can do more efficient decoding by doing the first couple of iterations, very high resolution computations, and then later iterations, you scale back and do use lower and lower resolution in the later iterations of the computation. You can get the same result with less power. So again, here's the same idea where we were looking at ways to automatically recognize when, we're almost done these iterations here. We don't need the 10-bit resolution anymore. Now we can get away with 4, or just do a couple more iterations and we're done. Be able to identify that dynamically with some of the research we were doing. But again, it resulted in, we did a prototype implementation, which is shown here. Again, it's pretty old technology, 0.13 micron technology, and it's because it was about 10 years ago we did that. But it gives you an idea for, that's kind of the scope of things that students can achieve in terms of integrated circuit design. So there's over 500,000 gates there. And at the time, it was the fastest LDPC decoder. Obviously, it's been way surpassed now. There's been a lot of interest in LDPC decoders and using much more advanced technologies, but that work is still cited there, so I'm quite happy with that. And here, just last little project I want to touch on, another PhD student working on this, which is on 3D time-of-flight imaging. The idea here is that we're considering the use of an array of single photon avalanche photodiodes that basically can detect the arrival of even a single photon and produce a pulse in response to that single photon. And so what we're really looking at here is using that type of array, which they're just being developed now commercially. The array sizes still currently are small, something like 64 by 64, but they're growing. There's a lot of R&D being pumped into that sensor array. So we're interested in the readout circuitry, the circuit that comes beside it that's going to basically read the time of flight out of this huge array of chips and know that, okay, from this photon arrived at this particular instant, and then collect that from all the array and then put together like a depth map, like an image, depth image from that. So these sort of arrays have the potential to have, higher spatial resolution over longer ranges, like the sort of silver bullet would be to get millimeter resolution over 100 meters, right? Just to give you a feel for how this differs from the kind of stuff that's, in the iPhone X famously or whatever, right? The idea is to get that kind of millimeter resolution over a much longer range. You need these very sensitive photodiodes to help you do that. But the circuit challenge is huge, because imagine you've got 1,000 of these, and now you need 1,000 readout circuits, all with sort of picosecond resolution refinement. That's the research challenge for us. So ultimately, this has just started in the past year or so. But the goal is to work towards a prototype where we could have an array of S pads. And then underneath that would be the circuitry that the student designs, which would be an array of time-to-digital converters that basically convert the arrival time of these pulses into a digital code, so you end up with an image, effectively a depth image, over this whole array. So that's just a quick summary of the activities in my lab. I got one more slide here. Come up for a second. But basically, I'm sure it'll come up in a sec. But basically, just summarizing the projects that we're working on right now. We're continuing to work on high-speed interconnect between chips. So we're looking at how to get the highest possible bandwidth over printed circuit board traces, cables, or even optical fibers. We also have and so that project is mostly in collaboration with Huawei. That's sort of separate from the Cohesa project, separately fun project I have there. Also working on broadband data converters, both analog to digital and digital to analog converters for wireless communication and things like 5G. So that's in collaboration with Analog Devices that has a local design center. And then I mentioned this 3D time-of-flight imaging application. So that's got a research partner here, Capic Integrations, a local IC design company. And then Cohesa, of course. So just a quick snapshot of what's going on. I'm always happy to follow up with anybody that's got questions remotely. You can always email me anytime. Email address is right here.
Thank you, Tom. So if we have any questions from the people that are remotely, you can post them on the forum. In the meanwhile, I want to ask in terms of, so for you it would be interesting to, if somebody could give you some hints as to, I need to send this bunch of bits, but these are more important than the others. This could be something that could be useful to you.
Yeah, that would be really interesting. Yeah.
So for example, when I have a layer in a neural network, I could tell you that, by the way, this is roughly the distribution of values, right? And these are much more important than these other values, right? That would be useful.
That would be really interesting, actually, yeah. Because, you know, you can, for example, protect some bits more than others with their correction. You can also just apply line codes differently. Line codes are not really error control codes, but just things that help reduce the raw bit error rate, even aside from coding, right? You can apply like a different kind of line code, and that would require more redundancy, so a little bit more overhead for those important bits, and much less redundancy than for the less critical bits. That would be really cool. How fine-grained?
I don't know. I guess this would be a question primarily for the people that do machine learning. I know this stuff superficially, but when you look at the distribution of these values, they tend not to be uniform. Some of them tend to have a lot of, there's a lot of clustering near 0, and then it really doesn't matter as much. And then there's also some clustering near large values, but usually nothing in between. For some layers. For others, it's different. I've seen stuff where there's 2 peaks. So it varies, but I guess it would be more of a question. I mean, we can do the studies, we can see what's out there, but I guess the more interesting question here would be if somebody in machine learning knew that you could give them different behaviors depending on the distribution, maybe they could train according to that.
Yeah, I guess I misunderstood it. Well, where I was thinking at first was this idea that you could protect or make sure that some bits were, you know, saved very carefully, you know, with a lot of robustness and so on. But you could also just do the non-uniform quantization thing, right? And just represent the levels that you're talking about with a certain code book. And say, you know, like in any levels in between, you just quantize it very coarsely, right? You just say, so we're looking at that idea as well as kind of having a code book, we call it, right? To interpret the code as being, you know, these non-uniform levels. And you reduce it into bits you need to represent the quantity.
Do you have any questions online?
I didn't notice anything. I'll just, we don't have anything from.
One last question. What kind of technology we have access to? So let's say we want to do prototypes. What kind of technology right now it's reasonable to expect to do prototypes on?
Yeah, 28 nanometers fairly straightforward to access right now. 16 nanometer we have access to via collaboration with Huawei. So it would be, you know, for discussion whether that would be could fit with Cohesa as well.
So maybe we can, thank you, Tony.
Sure.
So maybe we can move on to Arrvindh.
Arrvindh?
Yeah, just once. Can you guys hear me? I guess.
Yes, we can hear you.
Let me share the screen again. Alright, so hopefully this should work. Can you guys see the slides?
Yes, we can.
Alright, okay. So feel free to ask any questions as I go along. And
okay. Sorry for interrupting, Arvindh. I was asking whether they're being shown on the stream online. Thank you. Sorry. Go ahead.
okay, shall I go ahead?
Yes, please. Sorry for that.
Yeah, so feel free to ask any questions as I go along. Most of the tools that I talked about today are kind of available at this GitHub link. So I realized as Tony was talking that, in his world, the outcomes are kind of chips. In my world, the outcomes are kind of software tools. And so most of these are available at the GitHub. As Andrea sent me that email saying, make a quick introduction about yourself. I just wanted to quickly say that I am not a ML expert, not a circuits expert either. I'm basically a systems architect, and I make a living by putting things together. Most of the work, as the first slide kind of was jokingly showing, most of this is done by my awesome students, two of whom who've graduated actually, and funnily enough, they went on to work in groups within these companies that were ML groups. So even though their PhD work was not in ML at all. So I guess that kind of points out the pervasiveness of ML these days. I kind of had about 5 students in my group, 2 of whom graduated, and I have 2 new first-year students who are not listed here, but who are also going to be working on some of these things. That said, we have had ML work for about a couple of years, namely with local companies, and I'll kind of start off with that. So the work that I described today is mostly pertinent to Cohesa. There's other stuff that I do that is not pertinent to Cohesa that I'm not going to talk about. So the one thing we did with the BC Ministry of Transport is actually look at analyzing the flow of traffic. So this was a recent call for proposals that they put out. Which kind of started our work in Cohesa, where they have so BC at BC the traffic cameras are kind of open, and so they put out a database with for basically where you could see live images of traffic as it's going along, and the simple goal is to kind of detect how many cars are going through, how many buses are going through, check if there's an accident out there, and the key challenge with this is to do this real time. So basically, do 30 frames a second, right? And so what we set up for them was a cloud infrastructure, so using OpenStack. So we have a cloud instance running within SFU, within our department. It's about 500 nodes. Each node is maybe like 32 cores and a GPU. And in this case, what we were doing was essentially the images or the video, this is actually video streams coming in live, and you're expected to do line rate processing. Right? So the goal is to for example, you could imagine as traffic increases, essentially you got to whip up more nodes in order to meet the latency constraint. And so that's kind of the idea here. So the main innovation is in the cloud scheduler and all the work in putting together the system so that people can do a line rate ML. Right? And that was kind of the idea with that one. The other thing we did with a partner at SES was SES is a company that does building energy management. So they do building energy audits. So in this case, for example, this is a sample building. So you get each building these days typically has, this is just a sample example in terms of sensors and fans. And there are these open source platforms called Voltron. There's another one out of Berkeley called Boss. And all these guys provide a data interface to these sensors. So once you install, imagine one of these OSs on a Raspberry Pi in the building's network, you kind of get every 10 milliseconds you would get a data sample point, a 40-point value for each of these sensors. And essentially you get this a continuous signal stream. And the goal is to so previously what happens is when they do audits is, for example, SFU might recently employ these guys to come and say, hey, how efficient is our building running, right? And these are typically done by human beings who analyze these signal streams. Obviously, as you can kind of guess, there are many, many, many signal streams, and the anomaly detection becomes really hard by a manual process. So what we help them build is a ensemble learning for anomaly detection. Ensemble here refers to the fact that we use a bunch of PCA, SVM, as well as deep learning learners at the back, and then kind of vote to figure out which learner is kind of the best. And the idea is simply given a signal stream, find if it has an anomaly, right? So this could either be historical data or this could be live stream data, right? In both cases, the goal is to kind of figure out, basically define what an anomaly is automatically. So in this, in the human, previously when the SES was doing this, a human being is sitting there and they kind of using their knowledge to kind of define what an anomaly is. In this case, we just define anomaly as anything that deviates from normal behavior, right? Normal being we don't actually know what it is. And so we're using ML to kind of try to understand that. And also it becomes challenging when you have to analyze multiple stream sources. So not just look at, for example, airflow, but you may have to look at other sensors such as fans and windows kind of to try to figure this out. And so this is something we did for them. We continued. My actual work is actually not in ML, but I have, like I said, this work over the last few years. And based on these interactions, basically, it became very clear to us that there were certain things that are very important in ML these days. So one is latency is king. That is, you imagine doing ML at 30 frames a second. So latency rules supreme in many of these applications. Energy efficiency is king. So this may seem obvious, but in the level of energy efficiency that's required is what is really interesting here. So for example, SDFs is talking about doing ML right at the endpoints on building sensors themselves. And these sensors are like, imagine that they've got a processor that's typically a Cortex M3, if you're lucky, and they run at about 200 megahertz. They've got about half a meg of memory, and you're expected to run a training and prediction in that. That's small.
Arrvindh, can I? When we look at your slides, there is on the lower right corner there is a box that says colors that overlaps about 1/8 of your slide. Can you
give me 1 sec. Let me try to close that.
Where it says Zeph and the name. Okay, great. Thank you.
Did that go?
Yeah, but the slide is white now. So
okay. Okay, I got it. Did it play?
This is good, yeah.
Okay, all right. So the other thing that we also realized was the time to market is king in this space where effectively, algorithms evolve over weekends. People are talking about training at 1 to 2 bit quantizations. Models are becoming increasingly sparse, where different inputs are basically taking very different paths through these models. So people may want to prune or segment these even. People want to train with really small batch sizes, which apparently aids innovation in this space. And so people are talking about like 1 million batch sizes. And so one of the things you observe is that time to market is really important. That is, how fast you get from your algorithm to an actual implementation, possibly in specialized hardware or not. Yes. So based on these aspects, so my students and I mainly focus on building hardware from software. So essentially, how do you get some piece of custom hardware? So the previous weeks we've seen a lot of people talk about retrofitting GPUs with components that help with ML. In this case, we're talking about the custom part itself. It could either be retrofitted to a GPU, or in some cases it could be a separate part completely, right? And you could either be mapped into an FPGA or maybe even go into an ASIC. So in this case, we are interested in saying, here's a software program, or here's the actual ML algorithm in Python or C++, or some language, and then translating it to a hardware specification in Chisel, right, which is a new HDL. And the main reason that we want to do this is, if you look at the if you go back to my previous notions of latency scaling and energy efficiency scaling, then customization is kind of required. But if you look at time to market, then the key challenge is, why is time to market really high for hardware? And it turns out that in terms of cost and time, the biggest cost is obviously just design, right? And so there have been multiple people that have kind of spoken about this. This was a recent tape out of a chip from these guys called Open Celerity, so where they're looking at a custom chip versus a CPU GPU implementation for CNNs. And obviously performance to energy, even at the older technology node, the custom chip is better. But the key cost is just the cost. And the main contribution to cost here is design cost. So the man months kind of required to implement the hardware specification itself, given a software program. And so our main work is on making hardware design kind of easier, actually kind of not do hardware design by hand, but automatically. Right? And so in our experience, it's always been kind of about the language. Languages are quite different from the software to the hardware. There's lack of types. Hardware design inherently concurrent. It's verbose. And reuse is kind of hard in this space. So it's very hard, for example, to imagine somebody putting out a libc kind of library for hardware, where you can automatically start incorporating these in your own application. Composability is hard. So if you want to like straddle multiple libraries, it's even worse. Doesn't really help. There are modern languages that kind of help with this, but they still continue to structurally specify. So hardware design is inherently different than software. Right? Software is kind of an imperative step-by-step sequencing of step specification, while hardware design is kind of a structural specification. Right? And there's many man-months still required to comprehend and translate a software specification. Right? And our main goal is kind of to help people like SES come up with their own chip. Right? These guys employ maybe half a dozen software engineers. They don't employ any hardware designers at all. They have no idea about chip design. But our goal is to kind of enhance open source hardware design and kind of open it up to a whole bunch of different people. And this hardware can even be substandard, but it's substandard only compared to a manual implementation that might take many, many, many months. Right? So our main goal is to kind of speed up the whole feedback loop process of going from a software to a hardware specification. And the way we kind of do this is essentially built kind of an open source, strongly typed hardware sketcher. And this is kind of a bunch of different words. I'll try, in a short presentation, it's kind of hard to describe all the techniques. But the general idea is that we built a lot of infrastructure into the LLVM compiler. So you've got a full-blown compiler and what our tool itself is called SketchUp, which is like a tool that translates any compiler IR into a specification in Chisel. Okay? And Chisel is a new HDL that gets further translated into Verilog, and then the Verilog is what we're synthesizing. And right now we've mapped it to FPGAs. We've also pushed them through synthesis tools, in the synopsis tools, to kind of figure out what the power and performance numbers should be. Right? And at each level, we kind of can apply optimization. So you can apply optimization at the compiler level. We have optimization passes that, similar to writing a compiler, you write passes that optimize the hardware itself. So you write those at the Chisel level. And one of the main features of this is that it's entirely strongly typed. I'll give you an example of what that means in a second. But certain features you get with us is you get strongly typed hardware. You get hardware libraries. So, for example, you get libraries that you can reuse and compose in different applications. You get partial implementation, where some of the implementation could be in at the language level, like at the software, and then they might have gaping holes, right? And then you may fill in these implementations at the Chisel level. So I'll get into what that means more in a second. You again get functional verification because you're automatically translating using a tool from the software to the hardware specification. By verifying the software implementation itself, and the tool, you kind of can verify that the hardware implements what it is expected to, right? And finally, it leads to rapid prototyping, mainly as an artifact of the above four. So I'll actually give you an example before I go back to a high-level overview of why this approach is better, we think. But here's a simple C++. I'm sorry to put code out there, but this I'll just quickly explain. So this is just, I just pulled this up from today morning, but essentially you have an outer loop, and every time the thing is even, you're going to be performing a 32-bit integer add, and every time it's odd, you're actually going to be adding two matrices, all right? And essentially, in this case, you've got a templated add where you've got two adds. And the add for the 32-bit is kind of obvious and is specified in the software. But the add for the Tensor 2D, there is no specification software. So there is no implementation of Tensor 2D in a C++. I'm not saying that it doesn't exist. I'm just saying that for the purposes of this example, assume that there is the Tensor 2D's implementation itself doesn't exist in C++. Okay? And what happens when you generate a normal, when you pass this through a tool chain, is that you're going to get a hardware that kind of looks like this, where the hardware itself is built up using pieces. So it's not like one big giant gate level specification that is hard to parse and read, but it's actually generated in a hierarchical fashion where we basically separate out each type and we're generating the hardware for that. And we also have micro-architectural boxes for each component itself. So we have the logic box, which kind of implements just the data flow graph. We have data boxes that kind of translate all the loads and all of this. All of this is automatically generated. The key feature to all of these is that it is typed. So every node in this hardware flow graph has kind of a specific type. And the types can be arbitrary and are kind of user-defined. So for example, in this case, you have a 32-bit type, and you have another one that's kind of Tensor 2D. What happens is that for the 32-bit type, the implementation is kind of obvious, and you're just going to pull in an ALU to kind of do the job. But for the Tensor 2D, you don't actually have an implementation C++ yet. So nobody has specified how do you actually implement an add for Tensor 2D. What we do is we have a micro-architectural library that's written in Chisel or other languages. And from that, we kind of pull in the implementation for the Tensor 2D itself. So essentially now what's happened is you've got a C++ or Python or any program that can be translated to LLVM that's kind of specifying components, some of which may have an implementation in software, and some of which may have no implementation software, but only have an implementation in the hardware. And then we're kind of pulling these implementations in and stitching them together as we kind of go along. And we also, what this permits us to do is to optimize the program while leaving holes in it where we can fill it in kind of later. And we also can generate these implementations themselves. So the add Tensor 2D does not necessarily need to be written manually. And this is where the sketching component comes in. So in the programming language world, there's the notion of sketching, where given a specification, you can kind of generate different implementations for the specification. And that's how we kind of generate these functional units or operations for complex things like adding two matrices. And our main idea is, if you look at the existing way in which people kind of do specialization, so there's broadly two ways in which people do this. So one is behavior specific and the other one's kind of domain specific. So the behavior specific, people basically target a pattern. For example, a embarrassingly parallel or parallel map produce is a pattern. And people build in the compiler support and the hardware support for that specific pattern. And then it's the goal of the domain expert to kind of write their programs in such a way to utilize that pattern and map it to a specific hardware that also accelerates or specializes for that pattern. In this case, the end user effort kind of is one, how do you translate your domain's program to use that pattern? And the other one is finally building the pattern itself to the hardware. If you look at domain specific, then essentially what they do is each domain gets its own compiler and hardware. So example of this would be like TensorFlow, right? But if you have a different domain, or if the domain changes slightly, then you kind of have to re-implement all of it. So each of us is kind of duplicating the effort in terms of domain. So our main goal is to kind of sketch these domain-specific accelerators on the fly. So at least get a alpha version of the hardware specification out there really fast. So we have these different domains, each of which may have their own type system, and they provide the hints to the compiler through the data type system, which already exists in this program, right? So for example, if you go look at an ML library, it's going to be filled with types for linear algebra, right? So we kind of exploit that type system that already exists. And then the compiler kind of further optimizes or translates that and goes to a tool, links it with a set of microarchitecture library, which is independent of the domains themselves. You get them for different types, but obviously, hopefully, these are reusable across different domains, right? So if you have, for example, you can imagine like all the interface logic, for example, the memory system is kind of fixed, and you can try to pull that in. And then finally, when we self-assemble this, and then it's all completely parameterized. So for example, you can easily go from like a 2-bit floating point to a 32-bit floating point by changing a single parameter. And essentially, then you get different accelerator architectures. What SketchUp generates is Chisel, and we're really exploiting the power of Chisel as a language to kind of enable this hyperparameterization and polymorphism. Currently, what we're doing with respect to Cohesa is one, we're trying to do hardware design-driven network pruning, where we're essentially saying, okay, so you take an existing network, you kind of prune it, look at what the hardware is going to what the hardware might look like, and then go back and prune again. And the reason we want to do this is traditionally people who've done pruning have primarily used compressibility as their metric that they're interested in, but a compressed network might actually result in less efficient hardware behavior. So this was the recent result shown by Vivian at NIPS, Vivian's group at NIPS, and essentially what they showed was a compressed network, or the pruned networks may have more sparsity, and obviously sparse accesses lead to worse behavior on GPUs. And so in this case, pruning is not necessarily, different pruning strategies will lead to different behaviors. And so our idea was to try to learn what the pruning process itself should be like using Bayesian optimization. The other thing we want to do is also, I think Tor might have alluded to this earlier, where pruned networks do not scale up as well on GPUs as well as CPUs, and mainly because of the sparsity. And we've seen this as well with some of the codes that people locally have provided us. And one of the things we're trying to do is make a case for pruned networks on FPGAs. So if pruned networks show demonstrably better scalability on FPGAs, then FPGAs or ASICs might make a case for those systems in lieu of things like GPU. And finally, our goal is to kind of provide a compiler, as in the translator and hardware libraries, kind of in general for people who are building in this community. So we don't exactly know what people are building or what kind of innovations they're doing, but it turns out we believe that many of the components are kind of common, and hopefully we can kind of eliminate the effort required to build these common pieces and aid the overall process. And that is, I'll stop with that and then see if we can take any questions.
Thank you, Arrvindh.
Yep. Thanks.
Do we have any? We're running out of time. Do we have any questions on the line?
Online. I don't see anything.
So can we go back to the slide where you mentioned that Hotchip's quote?
Go back to the slide. Which slide?
The one where just before you started talking about your hardware synthesis environment, there was one slide where you're talking about what are the requirements for these networks, that they have to be done in 1 or 2 bits. Yeah, the next one.
This one?
No, we go back. Here, this one. So what is the input, what is the input of these networks you're looking at?
What is the input, as in, what do you mean by input?
Yeah, what do they process?
Oh, in this case, in the case of the traffic guys, you're processing video streams.
Okay.
And in the case of the building guys, you're processing like streams of data. Like for example, like this. In this case, it's looking at airflow data. So imagine like many such streams. So in this case, in the case of the building guys, it's just a bunch of floating point values, right?
So when you say down there, train at 1 or 2 bits, what are you referring to?
So in this case, this is not my statement. So I'm just going to talk about Jeff Dean's hardships talk, where I think slide 49 or something, he talks about training with, in some specific cases with smaller bit widths, and even like I think binary ones, just a single bit.
Are
right?
these the waste activations or both? You know?
What do you say?
Are these the waste activations or both? You know what he was referring to?
I think in the next slide, in the same, I can send you the link. But in the next slide, he does, in the talk, he refers to a couple of them. That, while speaking, he does, but not in the text. In the slides themselves, he doesn't say it, but while speaking, he does.
All right. Now, are these networks you're working on something you can share with everybody in the network, or these are for the time being proprietary?
So the ML itself is not proprietary, I believe. I can check. I think the network should be shareable.
Okay, all right. Let's follow up on that. So
because we are using standard techniques, it's just the framework we're putting together is comprehensive.
Perfect. Okay. So thank you, Arrvindh. We don't have any online questions, right?
No.
So thank you all for participating today. We're going to resume next year, which is going to be soon. I'll be following up with several of you, trying to entice you to give one of these presentations. We're probably going to do another set of series now soon. They're going to be more technical in the sense that not only get to know the team, but also let's review recent works that are interesting or works that people are currently doing and they're willing to share, like Arrvindh has done today, which is very nice of him. So thank you all, and we'll see you soon.
Thanks.